Alright, guys. Yeah, I made a video, but later I find I didn't record my voice in the video, so yeah, I have to remake it. Alright, so in today's class we're gonna start a new chapter, which is chapter 8, logical circuit. In this chapter, we're gonna start from the fundamental knowledge, such as what's the definition of digital signal, what's the definition of analog signals. We will also introduce logical gates and how to represent a logical expression by using logical gates. Um, and later on, we will introduce De Morgan's law, which is a tool or method to simplify a logical expression. Okay. Um, so in today's class, we're gonna start the fundamental things. We're gonna start with the basic concepts, such as what's the difference between the digital signal and analog signals, and we're gonna also introduce three basic types of logical gates. Before we start the actual lecture, uh, I want to mention some uh, assignments. First one is the homework 5 is due on this Friday, which is April. Let me check. Which is April 3rd. Okay. And some people ask me about the extension for homework 4. They need more time for homework 4. It is okay. Okay. Uh, if you need more time to finish your homework, just send me an email and let me know. And explain your reason for the extension, for the time extension. And I will always give you the time extension if your reason is reasonable. Okay. Alright, so in today's class we're gonna start with the basic concept of logical circuit. Let me first introduce the difference between the digital signal and analog signal. Okay. So for digital signal, it has two states, as I write it here. It has two states. One state is high, the other one is low. Okay. And for high state, we can use number 1 to represent, and for low state, we can use number 0 to represent. Okay. The signal amplitude. This plot shows the. Let me see if I can. Yes. All right. All right. This plot shows the digital signal, right? So from 0 to T1, as you can see, the signal amplitude is high, and from T1 to T2, the signal amplitude is low, or I use 0 to represent. From T2 to positive infinity, the signal goes back to high. So that's a plot of a digital signal. But for analog signal, it has infinity state. It has infinity states. That's the most obvious difference between a digital signal and an analog signal. An analog signal has infinity states, but for digital signal, it only has two states. Uh, a very typical example for analog signal is the sinusoidal signal. You can see from 0 to T1, there are infinity possible numbers for signal amplitude, right? Uh, and from T1 to T2, the same thing. You will have infinity possible values for signal amplitude during this time period. So what's the benefit of having two states in a digital signal? The benefit is digital signal is more robust to noises. Okay. So as you can see in this diagram, if let's say a digital signal is corrupted with some noises, and these noises this noise is not like the crazy noise. It's just like some minor noise, like some ripples on the original digital signal. So as you can see, we can still distinguish which part is high state, which part is low state, right? So we can still see the very difference between 0 to T1, which signal is located in high state, and from T1 to T2, on which the signal is located in the low state. So we can still distinguish the very difference between these two states. But if an analog signal is corrupted with noises, then there's no way you can recover the original signal from the noises, right? Like in this diagram, after I corrupt the original sinusoidal wave, the sine wave with some noises, the original value of this sine wave is heightened by the noises, right? So analog signal is not robust to noises. Once you corrupt analog signal with noises, then it's very hard, or sometimes it's impossible to recover the analog signal. But for digital signals, it's more robust to noises. You can still distinguish, or you can still tell the original digital signal from the noises. Alright. So is there a way to convert analog signal to the digital signal? Since the digital signal is more benefit in signal transmission, because signal transmission, if you transmit a signal through L, just like the example we introduced earlier about the radio station, right? When you transmit a radio signal in the L, then there's some external noises will corrupt your signal, right? So digital signal is a better choice to transmit information. Right, so how to convert an analog signal to digital signal? The simplest way is using a threshold, right? So like this diagram, this plot, the curve, like the random curve, is my analog signal. And I want to find the corresponding digital signal for this analog signal. You can define a threshold like this one, right? And from 0 to T1, the analog signal is above the threshold. Then I define this time period, the signal, the corresponding digital signal is in the high state, right? So I draw this diagram. From 0 to T1, the digital signal is in the high state. And from T1 to T2, the analog signal is below the threshold. Then I define the corresponding digital signal is in the low state. And from T2 to positive infinity, the analog signal goes back above the threshold. So the corresponding digital signal is on the high state, which is 1. Alright, so that's the digital signal and analog signal. And for the next topic I want to introduce is logical gates. Logical gates run with digital signals, right? In today's class, I will introduce 3 basic types of logical gates. The first one is AND gate. It's the AND gate. For AND gate, it has 2 or more inputs, and it has 1 output. We can use letter A and B to represent 2 inputs, and use letter C to represent the output. The schematic diagram for AND gate is presented as this one. The left-hand side is a straight line, and the right-hand side is a half cycle, right? In this AND gate, in this example, the AND gate has 2 inputs, A and B. A, B, C, all of these symbols or letters are digital signals, represent digital signals, okay? Which means A could be 0 or 1, B could be 0 or 1, C could be 0 or 1, right? The functionality of an AND gate is C, the output, equals to A times B, which is the multiplication of 2 inputs, okay? And here, the truth table. The truth table is a tool which lists all possible combinations of inputs and the corresponding output. Okay, for instance, for this two-input AND gate, it has four possible input combinations, right? Which are 0, 0, 0, 1, 1, 0, and 1, 1. In other words, this truth table has four rows. Okay. Based on the functionality of the AND gate, the output equals to A times B, which means for the first row, 0 times 0, the output is 0. For the second row, 0 times 1, the output is 0. Third row, 1 times 0, 0. 1 times 1 is 1, right? And here I give some experience formulas for the logical AND gate. What's the value for A times A? To figure out that, we can draw a truth table. For this truth table, it only has two rows because there are only two possible combinations for input A. A could be 0 or 1. And for two inputs, since two inputs are both A, so we have two A's here. And in the first row, 0 times 0 is 0. 1 times 1 is 1, right? So the output is still A. What about A times 1? Based on our previous knowledge about multiplication, anything times 1 is the original thing, right? So here, that experience is still satisfied. A times 1 is still A. We can verify that with a truth table. A could be 0 or 1. 1 is always 1, 1, right? 0 times 1 is 0. 1 times 1 is 1. So the output, as you can see, that is still A. How about A times 0? Anything times 0 is 0, right? And to verify that, we can draw a truth table. A is 0 or 1. 0 is always 0. The first row, 0 times 0 is 0. 1 times 0 is still 0, right? So the output is 0. And for the last one, A times B equals to B times A, which means if you swap two elements in the multiplication, the result doesn't change. Right, so that's the logical AND gate. Very simple, right? Right, so the next one is the logical inverter. The logical inverter has only one input and one output. Okay. To draw a logical inverter, you can use a triangular and the square. The left-hand side is the input, the right-hand side is the output. If the input is A, the output is A bar. A bar means not A or the inverse of A. So what that means? The truth table of the logical inverter is presented as this. A bar is the flip, is the opposite of A. So if A is 0, then A bar will be 1, which means the opposite of 0. That's A. That's 1, right? If A is 1, then the opposite of 1 is 0, right? So logical inverter will flip your input. Right, then what's the value for A times A bar, right? Here we use a logical AND. Here we use a logical AND to do the operation. A times A bar, one input is A, the other input is A bar. A could be 0 and 1. A bar is the opposite of A. So in the first row, if A is 0, A bar is 1. If A is 1, A bar is 0. 0 times 1, in the first row, 0 times 1 is still 0. 1 times 0 is still 0. So the output is always 0. And the second experience formula is what's the value for A double bar, right? A double bar is still A. It's just like if you flip a double-sided paper twice, then you will get the original side, right? The next one is called the logical OR gate. OR gate, okay. OR gate has two or more inputs and it has one output. The diagram, the schematic diagram for OR gate is presented as this. The difference between OR gate and AND gate is on the left hand side, right? For OR gate, the left hand side is a curve, but for the AND gate, the left hand side is a straight line, right? Alright, for the logical OR gate, it has two or more inputs. We use AB to represent. The output is C. Okay. And for the truth table of the OR gate, there are four possible combinations for inputs. In other words, there are four rows. If A, B are both zeros, then C, which is the summation of A and B, that will be 0 plus 0, that's 0. For the second row, 0 plus 1 is 1. 1 plus 0 is 1. For the last row, which is the tricky one, what's the value for 1 plus 1? Some people may say 1 plus 1 equals to 2. Everyone knows that, right? But here, in the digital signals, 1 plus 1 is still 1. Because digital signals only have two states, 0 or 1. There's no 2 in digital signals, right? So if you have a number larger than 1, that is still 1. Okay. Or in other words, if you have a signal, if you have a number higher than 1, that is equivalent to high state, and high state is 1, right? Alright, so be careful with this part. That's not 2, that's still 1. Alright, so here I give you some experience formulas. What's the value for A plus 0? A plus 0 is still A, right? Just like our normal summation. Anything plus 0 is the original thing. What about A plus A bar? A could be 0 or 1. A bar is the inverse of A, which could be 1 and 0. 0 plus 1 is 1. 1 plus 0 is still 1. So you see, 1, 1 is always 1. What's the value for A plus 1? A could be 0 or 1. 1 is always 1, right? So 0 plus 1 is 1. 1 plus 1 is still 1. What's the value for A plus A? A plus A could be 0 or 1. The other A is also 0 or 1. 0 plus 0 is 0. 1 plus 1 is 1. So you see the output is identical with A. So A plus A is still A, right? So that's the logical OR gate. Alright, so here we have introduced three basic logical gates. And sometimes we can use the combination of these three logical gates to represent a logical expiration. But before we reach that part, let me first give you the definition or the basic understanding of the Boolean algebra. Boolean algebra, okay. So the definition of Boolean algebra is operations on logic variables such as A, B, C that we introduced in logical gates. Those letters, those are logic variables. By AND, OR, and NOT gates. So Boolean algebra is defined as the operations on logic variables by AND, OR, or NOT gates. All right, give you an example. Simplify the Boolean algebra, the Boolean expiration. And draw the logical circuit. Okay. F equals to AB bar C plus ABC plus CD bar plus CE plus DD bar plus DE. Okay. So here in this expression, we have 5 logic variables, right? They are A, B, C, D, E. Those 5 logic variables are inputs, right? And the output is one logic variable, which is F, right? And for this expression, we can do some combinations. We can do some operations to simplify these Boolean expressions. Here we use Boolean expression is equivalent to logic expression or digital expression, because Boolean has 2 states, right? Boolean it could either be 0 or 1. So Boolean expression basically is not a new concept. It's very similar to digital expression or the logic expression. All right, so let's look at this Boolean expression F. Here, if you compile the first term and the second term, what you will find? They both have AC, right? A times C. So we can extract AC out, and then what's left is B bar plus B. B bar plus B. Right, so that's the first 2 terms. What about this term? D times D bar is what? In the logical AND gate, we give some experience formulas. This one. A plus A bar is 0, right? So here, D plus D bar is also 0, right? Then let's write the remaining parts. CD bar plus CE plus DE, right? What's the value for B plus B bar? B plus B bar is 1, as we mentioned earlier, right? A plus A bar is 1. A plus A bar is equivalent to B plus B bar. Here, symbol just means logic variable, right? It could be 0 or 1. So A plus A bar is 1. Then B plus B bar is also 1. C plus C bar is 1. D plus D bar is 1, right? Here, letters or symbols just represent a logic variable. Right, then AC times 1 plus CD bar plus CE plus DE. Could you restate the question? Yeah, I triggered the Siri, but never mind. All right, AC times 1 is still AC, right? Plus CD bar plus CE plus DE. Here, for the first 3 terms, we have C, which is the common factor or the common variable, so we can take it out. C times A plus D bar plus E plus DE, right? So that's the simplest expression of the original Boolean expression of the original F. So how to draw a logical circuit that represent this logic expression, right? So here, let's first count how many variables, how many inputs we have. We have A, we have C, we have D, we have E. We don't have B anymore, right? So we don't need to use the input B. The first term is C times A plus D bar plus E. So I need input C, right? And C is multiplied with another term, which means I need a logical AND gate because the functionality of AND gate is multiplication. But before that, I need a logical OR gate to sum 3 terms together. And these 3 terms are A, D bar, right? How to get D bar? We only have the original D, then we use a logical inverter to get D bar. And then we need a E, input E, right? So the output is A plus D bar plus E. Logical AND gate will multiply 2 inputs. So the output is C times A plus D bar plus E, right? And then for the second term, this one, we have D times E, which means we need another logical AND gate. 2 inputs. The first input is D, second input is E, right? And for this and for the output is DE, D times E. And then we just need to sum these 2 terms together by using a logical OR gate. So the final result, the output is F. Okay. All right, so that's how we represent or how we draw a logical circuit to represent this Boolean expression. All right, so let's end up here. In today's class, we have introduced the basic concepts of digital signals and analog signals, and we introduced how to convert an analog signal to digital signal by using a very simple method. We also introduced 3 basic logical gates, and we introduced how to simplify a Boolean expression or a Boolean or logical expression by using Boolean algebra, and how to represent that Boolean expression by using logical gates. Alright, in the next class, we're going to continue on this chapter and introduce the De Morgan's law. Alright, see you guys next time. Before we go, please remember the due date for the homework 5 is on this Friday. If you have any questions regarding the homework questions or this lecture, please let me know. Okay. Alright, see you guys next time.